streaming. Okay, so okay, so we're good. Huh? Oh, but it's on my screen, which is important as well. So we'll see whether this works or not. All right. Yeah, this is a different dongle compared to the other one, and I think this one may work a little bit better. We'll see. Okay, it's the projector went back to the other channel, so that's good. And close. There we go. All right. So the recorder is still on. You know, the recorder is really just recording a part of my screen. So even though you could not see, you know, the other part, it was actually still recorded. All right. So what we'll do is we'll take a look at a splitter and find out, you know, what it is and what it can do. A splitter is the first thing under wiring inside Logisim. So we'll just pick one out and look at all the different properties of a splitter. So every time you have a question about, you know, a particular component and want to know more about it, there are two ways to go about doing it. The first one is to go to help and go to the library reference and then check out how it is described as a component, which I'll do next. But the more intuitive way to do it, assuming you have already used a lot of features in Logisim, is to go to the property list of whatever object you have selected. So right here we have all of these properties. If it is displayed, it is probably something that can be changed. So keep that in mind. Okay, you know, all of these things can be changed, even though none of them display a little drop-down box symbol. So we'll just kind of go through this one by one. Facing, you know, just changes, you know, the orientation of the splitter, and that is referring to the split end. So in this case, the split end would be the blue wires. So by controlling north, east, southwest, you are basically saying where the split end is facing relative to the rest of the construct. Are we okay with that? Okay. The second one and the third one is a little bit more interesting and more confusing. So we'll talk about bit width first. So bit width in this case, you know, is it can assume any one of these numbers. I think all the way up to 32 at least, if not more. So bit width is referring to the unsplit end. Basically, how many bits is contained within that bundle of wires. So that has to match. If you have a multi-bit pin, like an input pin or an output pin, and you want to connect the unsplit end of a splitter to a pin or to a device that has a multi-bit port, that number has to match. Is that okay? If you have a 4-bit input pin, then this end, if you want to connect the merged end to that pin, then the splitter needs to also have the same bit width of 4. So bit width refers to how many individual bits is inside this bundle of wire on the merged end. Okay? So now we go back up a little bit and look at fan out. So fan out doesn't give you as many options. Well, it would appear to have as many options, but it's actually not true. Because what happens is you can split the wire into as many sub-wires or individual wires, well, I shouldn't say individual, into as many split ends as possible. Okay? So in the case, I'll give you one interesting example. Okay? So 2 and 2 is not interesting. So let's pick 4 and 2. There we go. So if you choose 4 and 2, that means the merge end has 4 bits, but you're only splitting it into 2 split ends. So what Logisim will automatically do is to do the average thing. So 4 divided by 2 is 2. So that's why it's allocating bit 0 and 1 on the top split end, and it's allocating bit 2 and 3 to the bottom split end. Is that okay? Does everybody understand the difference between what's a bit width versus what is a fan out? Okay. So once you have a fan out of 2, then you can do all kinds of tricks, because now you have 4 individual bits, and it cannot be finer in terms of what you can break it into, because these are the individual items. So what you can do now is to look into each one and say, I want this bit to go to which wire, or none at all. Is that okay? So you can, if I don't know why you would want to do this, but you can say none for all of them. So now you have a splitter that's basically useless, because none of the bits of the merged end appears on the split end. It's not very useful, right? But you can do it, okay? I'm just illustrating all the options that you have. Now, there's no need to say, okay, I have to allocate neighboring bits to the same wire. That is not a requirement either. If I wanted to, I can allocate bit 0 and bit 3 to the top wire, and then bit 2 and bit 1 to the bottom wire. That's perfectly okay. Now, why I want to do something like this, there may be a reason, there may not be a reason, okay? But that's what you can do. When you look at this notation, 1 to 2, that means if you look at this particular wire by itself, it itself can be split into two individual wires for bit 1 and bit 2 of the merged end. Now for the top wire, this notation says it is going, the first wire, the split wire from here is bit 0, the second wire is bit 3. So that's what that notation says. So is that answering the question, or do we need to go further?
That answers like half of it. Like,
okay.
What's the purpose? Is the purpose like you acquire these bits and then you can send it to other gates? Is that why you would split it?
It's because sometimes you need all the wires together, and sometimes you only need one portion of a bundle of wires. So this allows you to split a bundle of wires into individual wires, because you only need a few of those.
Oh, okay.
But it can also work the other way. So you can have a mechanism to come up with individual bits, and then through a merger, which is just the other way to look at a splitter, you can merge multiple bits into one single bundle of wires. Then you can use a multi-bit gate to process whatever is coming in.
Gotcha. Okay.
So it's bi-directional. There's no direction to a splitter.
And does it duplicate the bits?
Does it duplicate the bits?
Like in our lab, we had like a wire to an output.
It cannot duplicate bits, because each bit can only appear on up to one of the split end.
Okay.
So I'm not sure whether that's what you're asking.
Well, because we had like an output in our lab.
Mm-hmm.
We had an AND gate, and it went to an output of 4 bits.
Mm-hmm.
And then we had the splitter that split it and showed us 2 bits as well.
Yep.
So are those bits that it showed a duplicate of the output? Like, could you?
Yes, they are connected to the same bits of the output.
Okay, so you can essentially get 2 for 1 in a way, because you have 4 bits, but then you have 4 bits for your output that shows your output. Then you can also get another 4.
Yes.
Splitting it.
Yes, they are connected in parallel.
Okay.
Yep. All right. So are there any other questions? Let me show you what we can also do to with library reference. So the library reference is also organized kind of like how components are organized. Okay, let me just pack this first and then go back here. See how in the library reference, they also have wiring, gates, plexers, and so on, and they're in the same order. So if you want to look up what is a splitter, for instance, you just look up here, and it gives you a pretty detailed explanation of what that thing is. I personally have not read it, because I kind of already know what a splitter is. But if you want to look this up, you can actually read this document and get more information. Is that okay?
Yeah.
Yeah. So it's a great resource. It even refers to the user's guide, which is not the same as a reference, because the user's guide gives you an example, and it explains what is going on in that particular circuit. So that's also something that you might want to look into, when you want to find out, what a particular component is or how to do a particular thing. All right. So that's good. That's a good question because the lab for today also requires the use of splitters. All right, so let's go back to today's class. We talked about addition last time and we concluded already with binary number addition. The last topic that we talked about with this one was the very last expression that has like big and big or notations and whatnot. And I explained, how to unpack, those notations one by one so that you eventually get back to, what the expression should look like. So are there any questions with that particular discussion? No questions? Okay, so if you want to kind of re-watch that part, it is definitely recorded. I remember last time my computer went out of it ran out of battery in the middle, and then there were two parts. Okay, so there's part 1 and part 2 on last Wednesday, but part 2 definitely covers all the way to the end of the lecture. Is that okay? All right. So if there are no questions about binary addition, we're going to move on to binary subtraction. So if you followed your Canvas, the next available topic that you can read is over here. All of the other stuff you cannot read, you cannot see because they're not released yet. Okay, so what we'll do today is to move on to binary subtraction. And that's not what I want. Binary subtraction. I don't know where you put the module. Okay, there we go. Maybe not. I think it opened it up somewhere. Yep, there we go. Okay, so binary subtraction is all the way over here. And what we'll do is we will look into base 10 subtraction first. So this part here, the first part, especially this particular paragraph, the second paragraph from this section 3, talks about base 10 subtraction. So you already know that 9 minus 2 is 7 with no borrow. Or we can say it has a borrow of 0. Okay? And we also know that 2 minus 9 is, you can either say it's negative 7, or you can say it is 3 with a borrow of 10. Now, the concept of a borrow allows us to do multi-digit subtraction, just like the concept of a carry allows us to do multi-digit addition. Is that okay? So, do you think it is easier to learn subtraction, or do you think it's easier to learn addition when you're in elementary school? Addition. Why is it easy to learn addition? Well, carry is just as abstract, right? But the table is bigger with subtraction because addition is commutative, which means 1 plus 2 is the same as 2 plus 1. So the number of combinations you have to remember is only 1/2 of what you have to do with subtraction. Subtraction is not commutative. 9 minus 2 is not the same as 2 minus 9. So you have twice the number of cases to memorize in order to do subtraction. All right. So are there any questions about base 10 subtraction? No particular question? Yes, go ahead.
I don't really know how to word my question.
Go ahead. Give it a try.
Okay, so 1 times 10 is a borrow from the next digit.
Yes.
So you could say we borrowed from an imaginary 10 over by the 2, or?
Correct. So in multi-digit subtraction, the only thing you can do when you do not have enough quantity for the digit that you're responsible for is to borrow from the next or the more significant digit next to you. So that's why, whenever you're borrowing 10 in base 10, you're borrowing 10 because that's the base. If you're in base 2, you're borrowing 2. If you're in base 7, you're borrowing the quantity of 7. Okay, so I can give you an analogy, and some of you remember only the analogy but not the concept. But that's okay. That means it works to a certain degree too. So let's use this example, okay? 2 minus 9. I got $2 in my pocket, okay? And a bully outside of the classroom wants to collect $9 out of me. And I don't want to be beaten up. So what do? Well, I can call campus police, but that would defeat the purpose of this whole discussion, right? So let's say I do not call the campus police, okay? So what I'll do is I'm gonna borrow $10 from one of you, okay? So you say, okay, Tag, you can have my $10, just return it at some point, right? So now I have $12 in my pocket as I walk out of the classroom, right? The bully is gonna take the $9, and how much money do I still have left in my pocket? $3. So that's why 2 minus 9 is 3, but with a borrow of 1. That so-called 1 is actually 1 of 10 because you borrow from the more significant digit. Is that okay? Sort of? Go ahead. Not understanding?
I understand the analogy.
I think, well, 2 minus 9 in that example is 3, so how do we get the 7?
Well, the 7 is still, it's it's -7, but I think I got the number wrong here. Yeah, so I got the digits wrong. So you have to change it to 2 minus 9 is, wait, it is -7, which is 3 minus 10. So this 7 here should be a 3. Yep. So 3 is the result, but the 1 times 10 is a borrow. So let me fix this first. And now you guys can see firsthand, how I write notes, for this class. And all of my classes, actually. And which module is this? 284. And we are looking at results and borrow. And we are particularly trying to address the 7. There we go. As a result of 3 and a borrow of 1. There we go. All right. Let's see if that works. Yay. Thank you. Thank you for pointing that out. Okay. So now it is correct. 2 minus 9 is 3, but with a borrow of 1. So after the correction, are there any other questions? I challenge any publisher to be able to correct text in this particular manner. It still took me 30 seconds or so? Is that okay so far? Okay? All right. So subtraction is not commutative, but in base 2, we'll take a look at these cases, okay? See if they make sense. Does it make sense that 0 minus 0 is 0 in base 2, just like it is in base 10? Okay? Does it make sense that 1 minus 0 is 1, even regardless of the base? In base 2, base 10, base 7, they all work out the same way. Okay? 1 minus 1 is a 0. Does it make sense? Cool. So the only one that is tricky is what if we have 0 minus 1? In base 2, 0 minus 1 is 1. The result is 1 with a borrow of 1. All the other 3 cases have a borrow of 0. This is the only case when we have a borrow of 1. But it kind of makes sense, right? I have no money in my pocket. the bully outside wants $1, okay? So when I borrow, remember, when I borrow, I do not borrow the same unit as myself. I have to borrow in the unit of the next significant digit. So when I borrow in base 2, I'll be borrowing $2. So now I have $2 in my pocket. I walk outside, the bully takes 1, and I have $1 in my pocket. That's why the result of 0 minus 1 in base 2 is 1. But it also has a borrow of 1. So, yeah, go ahead.
In base 10, a negative number would be like the result of the borrow plus what you have. Or
So the negative value associated with a single digit subtraction is going to be the result minus the borrow times the base.
gotcha.
And it works out in any base, including in this case. So let's check it out. So 0 minus 1 is 1, but the actual quantity of the result is the result plus, the result minus 1, the borrow times the base. So in this case, the result is 1 minus the borrow times the base, which is 2. 1 times 2 is 2. 1 minus 2 is negative 1. 0 minus 1 can be seen as negative 1. So that way of looking at things does work out. Just like it works out in this case, 2 minus 9 is a 3, but since we have a borrow, the borrow is a 1, but we have to multiply the borrow by 10. So we have 3 minus 1 times 10, which is negative 7.
So it's just the way we represent it.
Just the way we look at it.
Okay.
In other words, when I walk out of the door, okay, when I walk out of the door with $1 in my pocket, what is my net worth? My net worth is not $1 because I owe someone $2, right? So my net worth is still negative 1. It's just that there's $1 in my pocket, but on paper, I still owe someone $2.
So negative numbers are more of an abstraction.
But it's,
Just a different way of looking at it.
I see it as no more abstract than a carry.
Okay.
Yep. Because if you look at borrowing as I don't have enough money, so I have to borrow, a carry is kind of like I have excess, so I'm lending it to the next more significant digit. But I don't want to turn this into a finance class. So are we good with this table? Is everybody convinced about the result and the borrow bit functions in base 2? So we are focusing on base 2 with this portion of the discussion. Are we good so far? Because if we are not, we should spend more time here just to make sure that we understand the concepts. Okay, I'm not seeing any questions. So shall we move on? Yes, go ahead.
What if you have a strange base, like you're not in base 2 or like base 10? Like what if you're in base 13 or something?
You can still, it still works the same way. It still works exactly the same way. The only tricky part about base 13 is we only have digits from 0 to 9, so we'll have to borrow, usually we borrow from the alphabet, like letters from the alphabet, so we'll have to borrow A, B, and C, in which case A is representing the quantity of 10, B is the quantity of 11, and then C is the quantity of 12. Then we'll be able to work out exactly the same thing. Is that okay? Okay, all right. All right, so let's move on from here. And of course, this last sentence here is entirely true. Okay, base 2 subtraction is far easier to learn compared to base 10 subtraction because there are only 4 cases. Okay, and some people like you would basically say, but the first 3 cases are totally trivial, okay? It's just intuitive, trivial. The only tricky one is the 4th case, right? But in base 10, how many items do you have to memorize, even if you ignore the so-called trivial cases? The trivial cases would be something minus 0, okay? Those are all trivial cases. Something minus itself can also be considered trivial. You still end up with a pretty large number of cases that you actually have to memorize in base 10. Okay, and that's one of the difficulties of teaching in elementary school is you have to have students to memorize, these things. Okay, some students are very good at memorization, and other students are not so good at, memorizing things. Okay, I can understand the concept, but if you ask me to memorize, just numbers and go like this and this goes along with that, it would take me a long time to do it. But in base 2, it's not that hard, right? I mean, it's pretty simple when it comes to learning subtraction. In this class, many of us will feel that this is actually difficult. That's only because we have learned base 10 already, and we instinctively just think in base 10. But base 2 inherently is actually easier. All right, so the next section, section 4, is basically saying, okay, this is all good, okay, but these are all arithmetic concepts, okay? The concept of result and the concept of a borrow are arithmetic concepts. They are not Boolean, they are not logical concepts. But since inside the computer, we can only deal with logical constructs, because we have already shown how to use 4 transistors to make a NAND gate, and a NAND gate can be used to make any logic gate, can be used to make logic gates to implement all of the Boolean operators that we are used to. Okay, but that's kind of the extent that we understand now. I mean, the computer can do and or not, and that sort of stuff. Okay, it can do it really, really fast too. But it cannot handle subtraction. It doesn't handle the concept, the arithmetic concept of borrowing and the result. So what we want to do is to look at the result and ask, well, can we replace this function with a Boolean function that gives us exactly the same thing? In other words, can we come up with an expression so that, if I pass the 2 parameters x, y, it will give me exactly these particular values. And you might notice that we have seen it already. Is this R function any different from the R function in binary addition? 0 plus 0 is 0, or the result is 0. 1 plus 0 has a result of 0. 0 plus 1 has a result of 0. 1 plus 1 is the only one that's kind of tricky because it also has a result of 0. But wait, that's exactly the same as what we're looking at here, right? So that means how we have handled the result function for binary addition is exactly the same way we handle the result function in subtraction. And that is also why I don't even bother to change the name of that function, because it is the same function. Are we good so far? Now, this is also in part thanks to using base 2, because in base 10, those functions would be different. Okay, the result of a subtraction versus the result of an addition would not be the same. But in binary, well, they turns out to be the same. So this is nice because we can use exclusive or if you prefer, we can use the long way of doing it in just and or not operators. But when you look at borrow, it is not the same as carry, okay? Because when you look at borrow, the only time we have a borrow of 1 is when the x bit is a 0 and the y bit is a 1. Darn it, we cannot just use the carry function, which is just a conjunction, right? So instead of using just a conjunction, I propose that we change the borrow function, or we define the borrow function in binary to just the negation of x and y. Would that work? Well, we can always quickly double check and make sure, right? So we look at the first case, okay? We have 0, 0 here. The negation of 0 is a 1, but this is also a 0, so we have 1 and 0, which is 0. That's what we want, okay? It works out. We look at the second case. The negation of 1 is 0 and 0, so we have 0 and 0, which is 0. Yep, we got what we want. We look at the third case. X is a 1, the negation of that is a 0. Y is not negated, and then we add those two, so we have 0 and 1. That's also a 0. That's exactly what we want. We look at the last case when we have x being 0, y being 1. The negation of 0 is a 1. 1 and 1 is 1. Oh, that's exactly what we want. So we can now, we just double check to make sure that the logical expression of not x and y implements the borrow function in binary subtraction. Now this is monumental in a way, because this tells me that, oh, so you're telling me that we can use Boolean operators to implement the arithmetic function borrow in binary subtraction. And yes, that's exactly what I'm saying. Is that okay? So we do not need to use arithmetic operations anymore. We're now translating everything to binary operations, or Boolean operations, or logical operations if you want to use that word. They're all kind of equivalent in this context. So are we good so far? Okay. All right. So what about multi-digit subtraction then? Okay. So let's take a look at multi-digit subtraction, just like we looked at multi-digit addition. And this time I will, okay, I'm going to use a text editor and see if that's a little bit more efficient. Okay. Okay, so before we abstract things into just, x2, x1, x0, let's do a base 10 subtraction first, okay? So we have a 9, 0, 2, minus, I don't know, 1, 0, 5, okay? All right, so I'm going to use the same method and the same notation as in addition. So I'm breaking this up into two subtraction, or smaller subtractions. So this is the result, okay? This row is still called Q, okay? So what is 2 minus 5? What is the result of 2 minus 5 in base 10? No. It's 7 with a borrow, right? So it's a 7 with a borrow over here. Yes? Just think, if I have $2 in my pocket and the bully wants 5, okay, and I borrow 10 from one of you, I have 12. When I walk outside, the bully takes the 5, I have 7 in my pocket. So the 7 is the result. Okay? This one, usually it is assumed 0, so we'll just kind of maintain it to be 0. And in the discussion of subtraction, I call this row T because it really is not the same thing as a carry, so it is distinct in this case. And now we have 7 minus 0. What is the result of 7 minus 0? Come on, you guys know that. It's just that. That's right. Okay. So moving on to digit 1. 0 minus 0 is a 0. It does not contribute a carry yet to this position. But then we have 0 minus 1. Where is that 1 coming from? That 1 is coming from? Exactly. It's because of the borrow of the least significant digit subtraction. 2 minus 5 gives me that one, that borrow of 1. So now I have to say, well, the $10 digit, you really is owing 1, okay? Somebody borrow 1 from you, but since you don't have anything, you have to borrow now from the 100th. Is that okay? So now we have to look at 0 minus 1, the result. 0 minus 1 has a result of 9. Very good. 9 minus 1 has a result of 8. 8 minus 1 has a result of 7. So that's kind of a longhand way to do multi-digit subtraction. I know most of you do not do it or write it out this way, but this is the way that I want to spell it out because this gives us a clue of how to make circuitry to get this to work. Is that okay? All right. So the next slide, or next to this, I'm going to say, okay, let's make this more abstract then. We have x2, x1, x0 to represent the value of x. And this is the value of y. It is represented by the same, by 3 digits. We have y2, y1, y0. So we have a subtraction of these 3. All right. And then the next row, I'm going to use the Q notation, just like I used the Q notation in multi-digit addition. So we have Q2, Q1, Q0. And then here we have T2. Well, actually, we have an overall T3, T2, T1, T0 for the borrow bits. And then the last one, we have a D2, D1, and D0 for the difference bits. Okay. So now the question is, if I just look at a QI, how do I define a QI? Well, we already know it's the result of the subtraction of the digits above that, right? So we start with this. It's the result of subtracting y1 from x1. Is that okay? What about ti then? Or ti plus 1? In other words, I look at t1, or I look at t2, okay? I look at this one here, and I ask, well, who can contribute to this borrow bit? Well, we have 2 places, right? Because x1 minus y1 can contribute to t2, but q1 minus t1 minus q1 minus t1 can also contribute to t2. So they can both contribute. So that means t subscript I plus 1 is the borrow bit of x1 minus y1 plus the borrow bit of q1 minus t1. Oops, I should change everything to I. Yep, go ahead.
So plus in this case means or?
No, this is arithmetic addition.
Literally plus.
Yeah, it is just a regular plus. Yep.
So it has to be a 1 or I mean,
No,
if
it's
one
just
is
plus.
correct.
It allows both to be ones. And then we just have a 1 plus 1 equals 2 if both have ones. The question is, can they both be ones? So now we have the d bits, okay? di is just the result of qi minus ti, so that one is rather easy. Haven't we seen something like this before? I think the last time I did this, I was handwriting it, so it may not look exactly the same, but in terms of concept, have we seen something like this before? Yeah, addition is almost exactly the same. The only part that is different is in here we use the b function for borrow, but in addition we use the c function for carry. That's it. Wow. The r function is exactly the same in base 2. Okay, so this is in base 2. So now the question now is, okay, so if we're going to specialize in base 2, what is this going to look like? Well, if we're specializing in base 2, the r function is exclusive OR, but the longhand of doing exclusive OR is not xi yi or xi not yi. Okay, I hope you guys still remember this. This is the kind of longer expression to do exclusive OR. This one here is a little bit tricky. Okay, so I'm going to write it out like this. It is not xi yi, and then we have a plus question mark here. And then the next one is qi ti, not qi ti. Okay, not qi is one thing, ti is the other thing. Okay, but since I cannot do subscript, this is the way it looks like. I put a question mark here because I'm asking, is it addition or can we use disjunction? Okay, so we had that question with addition before, and we have the same question for subtraction. So we'll resolve that question later on because we just want to handle the last one here, which is pretty easy. So this one is the result of qi ti, result of subtracting ti from qi, but we already know what this looks like. It's not qi ti or qi not ti. Okay, so we know what this one looks like already. So our focus is now going back to this part here and ask, well, can we actually use addition or can we use disjunction in place of addition? So the way that we do this is we look at this, and then what we do is we expand it. Okay, we expand QITI. So this is the negation of QI, but we know what QI looks like, which is from the previous row, which is not XI or XI not YI. And I have to be careful to put a negation on the entire disjunction. So this entire thing is QI. Is that okay? Does everybody see why the highlighted text here is just QI? All you have to do is to look up one line. Are we good so far? Okay. All right. So we take the negation of this and we end it with TI. Okay. So now the question is, how is this helping me? It is helping a lot. Okay. Because how can I make this part, okay, let me just highlight which portion I'm talking about. How can we make this part a 1? There's only one way to make it a 1, right? Xi has to be a 0, and yi has to be a 1. Very good. Okay, so let's say this side is a 1 already, but that locks in what xi and yi should be, right? Xi has to be a 0 and yi has to be a 1. Are we good so far? So we now plug that into this side here. Okay. So we now plug that in here. Isn't this exactly the same thing as the left-hand side? Isn't this part here exactly the same here? It is. Okay, so this is guaranteed. If this is a 1, this is now guaranteed to be a 1. And then some people will say, but Tech, that shows that both sides can be 1s and we're done. Wait, this whole thing is inside a negation, okay? But we are not done yet, because this one has to be ORed with this side here. I don't even care what that is. Because if you have a true already in the disjunction, the whole disjunction is going to be true. Are we okay so far? So now we extend the highlighted portion, and then we say this whole thing is a 1. Because the first part, the left-hand side of the disjunction, is a 1 already, the entire disjunction has to be a 1. Yes? Oh, but this whole thing is inside a what? A negation. Very good. So we look at the negated version of this whole thing and go like, oh, that just turns our 1 into a 0. Do we have any hope to make a 1 in this case? There's no hope, because this 0 is ended with a TI. It doesn't matter what TI is. TI can be a 0, TI can be a 1, but once I have a false in a conjunction, the entire conjunction is guaranteed to be false. So now I have just sealed the fate of the right-hand side of this plus question mark, operator. That has to be a 0 if the left-hand side of the same operator is a 1. Are we good so far? Oh, so that means, they cannot both be 1s. Is that okay? Is everybody convinced that not both sides can be 1s? If they cannot both be 1s, then we won't have a case of 1 plus 1 anymore. We can have 0 plus 0. We can have 1 plus 0. We can have 0 plus 1. But we won't have 1 plus 1. If we don't have 1 plus 1, then the OR operator and the disjunction and the addition operator will do exactly the same thing. Are we convinced? So that means now we can conclude and just say that, okay, so we can now conclude that this is really just an OR. I'm just going to use the earlier form, which is less typing and a little bit more clear. So now we can lock into just an OR operator instead of a confusion state of, well, is it or is it addition? Nope, we don't need to use addition. How is that good news to me? Yep. because it's a disjunction, and it's a very simple thing to do. Okay, I just need to do a disjunction instead of an addition. Now, if we needed to do an addition, we know how to do addition already because we know how to do binary addition. But that's a lot of unnecessary work in this case because we can just use a disjunction. But wait, I think we had a similar argument like this for addition. To, it is exactly the same kind of stuff. So what is the difference between subtraction and addition? Tell me. Okay, so let's see for each row whether we see a difference. Do you see any difference in terms of the Q, how it is different from how the way we define the Q term in addition? Nope, it's exactly the same. What about the D? It's exactly the same. So the only difference is the T, right? So what is different about the T versus the K? Because I call these terms K in addition. What is the difference?
Oh, it's using borrow.
The borrow is without this negation and without that negation. The carry, okay? When we had carry, it would just be xi,yi without the negation of xi. It would just be qi,ti without the negation of qi. With subtraction, we have just that additional negation to the first part of the conjunction. That is the only difference between addition and subtraction from the perspective of a binary implementation or logical implementation. Is that a good thing or a bad thing? It's great because we can reuse a lot of things that we already know and apply it here. So I'm going to challenge you guys to make your own borrow ripper subtractor. Okay, so you have to make a half subtractor first, and you combine two half subtractors to a full subtractor, and then you have to daisy chain your full subtractors to make a multi-digit subtractor. Okay, but if you follow the logic of how we made a multi-digit adder using full adders, and then we divide a full adder into two half adders, it is exactly the same construct, it's exactly the same structure. It is just that, oh, this thing here has an additional negation over here, then that thing does not. That would be the only difference. What about the carry ripple thing that we worked on just last Wednesday? Can that concept be extended to binary subtraction as well? Well, let's check it out. So now we have a borrow look ahead mechanism, and I'm going to show you this thing here. Okay. This one is slightly longer than the other one, but nonetheless it is close. Okay, let me see if I can fine tune. There we go. Excellent. Okay. So if you ignore all the stuff in between, okay, the bottom line is t subscript I plus 1 is now derived to be not xi, yi, or not xi or yi, the whole thing, and ti. Is that okay? All right. So we'll get back to this derivation later, but for now, we'll just trust tech and say that this is okay. This derivation works. Okay? But we'll come back and look at this. All right. So given that we are defining ti plus 1 to be this, I'm redefining g and p this time. Okay? If I redefine gi to be not xi, yi, and I redefine pi to be not xi or yi, don't we end up with the same thing that we had before? The exact same thing. Do you remember this from the discussion of carry look ahead adder? Yes? I hope so. Okay? What is the difference? There is a difference between this equation and the equation that we looked at in binary addition. What is the difference? Exactly. It's a notation difference. Instead of k and k over here, we now have t and t over here. Right? So do you think we can use the same method to expand T1 and express it using PG and T0 in this case? What about T2? Can we look at K2 and just say, replace all K's with T's? We're done. What about T3? I mean K3. Can we do the same with K3 and turn it into T3? K4. It's just replacing a character with another character, and we have the same thing. Isn't that cool? No one.
I think so.
No one seems to be excited. This is like super duper cool, right? It's not just cool. This is like super duper cool because all of the stuff, all of the difficult things that we did with the general expression, it looks exactly the same here. The only difference is instead of looking at K over here and K over here, we're looking at just T over here and T over here. The way we structure the P's and the G's and how we do all the conjunction and or all of those conjunctions is exactly the same. Okay? But you have to remember there is one fundamental difference between an adder and a subtractor. It is how we define G and P. The way we define P and G in an adder is without the negation. The way we define P and G with a subtractor is with that one extra negation. That's it. That's the only real difference between functional difference between an adder and a subtractor. So you build all of these complicated circuits for an adder. You just have to say, oh, I'm just going to have this one little switch here to decide whether the first term is negated or not. Now we can turn an adder into a subtractor. I think that is really cool. So are we good so far with binary subtraction? Yes, because the most complicated part of a carry log-ahead or borrow log-ahead are these conjunctions and the disjunction of the conjunctions and that whole mess, right? That is the bulk of the circuit. Whether you negate x first, that's an easy circuit to do. Okay, that's like lightning fast, and you can just do it just like that. Minor change of the circuit. So you can reuse all of the bulk of the transistor of a 64-bit adder / subtractor. All of that can be reused. You just have to switch one little thing at the very lowest level to control, are we negating x first? If we are subtracting. If we're not, we're adding. So that means you can reuse silicon a whole lot. When you sometimes you can add or subtract using the same group of transistors. And that is really cool. Are we good so far? So looking at okay, so we still have to go back and check whether tax logic is right or not, okay? This is something I want all of you to remember, at least with my classes. You always question tax reasoning, okay? Not that I intentionally try to deceive anyone. It's just that sometimes I make mistakes, just like earlier, okay? 2 minus 9 is 7. What? Well, I made a mistake. It's as simple as that, okay? So let's check this logic and make sure that, it makes sense. First row to second row. Is that okay? That's just how the B function is defined, the borrow function, okay? From the second row to the third row, that's just how Q is defined. We expand Q, okay? From the third row to the fourth row, we are using De Morgan's law. Okay, this is De Morgan's law. I take this negation on the outside and the conjunction on the inside. I apply De Morgan's law. It becomes this. Okay. From the fourth to the fifth, I apply De Morgan's law again. This negation on the outside with this conjunction in the inside. This negation on the outside with this conjunction in the inside. I apply De Morgan's law, and it turn each one into a disjunction and dissolves the negation. And then from the 5th to the 6th row, okay, I use distribution, okay. I just, is it called, how is it called in normal algebra? Huh? Foil, okay. So I just do a foil, but in Boolean algebra. So we end up with this. But once we have this, from the, oh, I'm losing count pretty quickly, 6th row to the 7th row, not xi is just false. Does it make sense? Because in a conjunction, you have one term and a negation of the very same term. So that means one of those two has to be false and one of those two has to be true. But when you're using a conjunction to connect those two, then you're guaranteed to be false. Okay, so I have a false here, and then from this row to the next one, I guess from 7th to 8th, we basically just get rid of the 0 or and the 0 or. Does that make sense? 0 or true, true. 0 or false is false. So that means 0 or by itself doesn't do a single thing. Let's get rid of it. Okay? And then from here to here, I use the same trick that we did before, introducing a and true, okay? And then from here to here, we use the same trick as before, because true or whatever is always true. So I just say true or ti, okay? And then I expand it out, and then I reorganize a little bit, and then I factor. After I factor, I identify these two to be just true. I identify these two to be just true. Then I end up with this one, the second last row, and then from the second last row, I did another factor to get to the last row. Now you can ask, well, that looks kind of long. Is this the fastest way to do this proof? I don't know, okay? I just did it once and go like, yep, I did it. I did not optimize it. So there might be a shorter version of this proof, but this is one. Are we doing okay so far? So once again, in this class, I will not ask you guys to prove like this. Okay, it is an exposure to Boolean algebra, which you will need in cisp 440. So look at this just like a preview of cisp 440 when they start to talk about Boolean algebra. Are we good so far? This is pi needle. We just took a bunch of pi needles and started counting and categorizing the pi needles. Is that okay? So let's take a step back, okay, and see what we have in the forest in this case. We started off with the lowest possible level construct, which is a transistor. It is a physical device. You can actually buy one, right? You can put it into a circuit. You can make things out of a transistor or a bunch of transistors. Okay? And then we say, well, but if you hook up 4 transistors, 2 p-type and 2 n-type, in this particular way, it behaves exactly like a NAND gate. It is a NAND gate, okay, which is a negated AND. And then we talked about how you can use NAND as an operator to make up normal negation and OR, which are concepts that you have already learned in cisp 360, right? So we're building from very physical, low-level devices to more and more abstract things that we normally do, right? So from and or not, we went through a whole bunch of derivations and whatnot, and we came up with the design of carry ripple adder as well as carry look ahead adder. Okay, the mechanism is kind of I'll call it tree branch level, okay? But when you look at the whole tree, what is it? Well, we can now use transistors to implement an adder. We can add binary numbers now. Okay, yep.
I think this is the first time you said ripple adder. What is a ripple?
Carry ripple adder.
Yeah, what is a ripple? I know what a look ahead adder is. What is a ripple adder?
That's the one that you make up of, that you have 2 half adders, you make up a full adder, and then you daisy chain a bunch of full adders. That kind of adder is called a carry ripple adder.
And the parallel one is the look ahead.
That's called a carry look ahead. Exactly. Yep.
Weren't you going to show us actually the carry ripple adder at some point? That was one of the exercises.
Oh yeah, sure. Yeah, I can certainly do that. I actually did that with the Tuesday, Thursday class. So if you cannot wait until I disclose it in this class, you can kind of look into the lecture of that class. But I will do it once at least in this class. So kind of put it on an item, of to-dos, right? But getting back to this, Forest. So we talked about addition, and now we just finished talking about subtraction. So not only can we do addition, we can also do subtraction. So that's where we are at this point, okay? Because being able to add and subtract is a big deal, okay? Because what do you think your super duper Intel processor can do at the kind of the, not exactly the lowest level, but at a lower level? It adds and subtracts, okay? Really, that's the only calculation it knows how to do, okay? Yes, I know there's bit shifting and some of the other stuff too, but primarily, adding and subtracting is what most processors know how to do natively. Then you might ask, but what about sine and cosine, power, exponent, and all those complicated things? They're all built from adding and subtracting. What about multiplication and division? They're all done by addition and subtraction. Okay, so once we have addition and subtraction, we have the basic engine, to implement most of the math stuff that you want a processor to be able to do. Is that okay? Yes? Go ahead.
I'm curious, can you build an AND gate out of, like, not NAND, just out of transistors? Does it have to be from NAND?
You can build an AND gate out of NAND because you can take the output of a NAND and then negate that. But negation can be done with NAND as well.
Right. Can you build it without using NAND? Like, is there a way to use transistors to build AND?
Yes.
Okay. So not all AND gates are necessarily built from NAND.
That is true.
Okay.
Yep. And I don't know how to do it. I just know that it is possible. But in this class, I'm not as concerned about efficiency as I'm concerned about conceptually can it be done. Now, obviously in industry, you worry about efficiency, but in this class, we are focusing more on the concept, and we feel that it is already a jump in terms of concept if we can connect physical device to conceptual things that we can do. But that's a good question. You can probably look it up and just look up conjunction in transistors, right? Cool. Are we still good in terms of addition and subtraction? Okay, so let's do that carry ripple adder. Wait, okay. How many people did this on your own already? Made a carry ripple adder. Okay, how many people tried? Very good. All I really wanted is for you guys to at least give it a try. Because in the attempt of trying, you're already trying to understand the concepts. So even if you don't have enough time, I got calc homework, I got physics homework, I don't have time to do something that is not graded. I understand that, not a problem. But as long as you spend some time to try to implement it, to try to solve the problem, you're already exercising. That to me is studying. I mean, this class, because it's open book and open notes, you don't have to memorize anything. It all has to do with understanding of the concepts and being able to apply that. All right, so let's go ahead and do this part here. I think we have more than enough time to do it, unless I make some really stupid mistakes. So we'll add a circuit. We'll call this a half adder, HA. And a half adder has 2 inputs and 2 outputs. So we'll take 2 inputs here, and then 2 outputs over here. So as I do this, you can kind of think about, what if I want to build a borrow ripple subtractor? Okay, just kind of think about it as I build this circuit, okay? So what I'll label this pin to be, okay, for the lack of we'll label this X and Y, okay? And then I'll label this one as the result of adding X and Y. And then I'll label this one as the carry of adding X and Y. Okay, this is a half adder. Remember, it's not a full adder. So let me switch back to maybe not. Okay. So how do I get the result? If I'm lazy, I can use an exclusive OR. Okay. But exclusive OR can also be built using just regular AND or NOT. So let's build an exclusive OR from parts. So we go to project again, we add another circuit. We call this exclusive OR, which is usually called XOR or EOR in some cases, but in most cases it is XOR. So exclusive OR needs two inputs. Okay, 1, 2, and it needs one output pin. Okay, here's my output pin, and then we need two AND gates. So we go to this AND here. And I don't like it when their default is too big and too many input pins. It's not too big of a deal. Okay, we put one here, we put one over here. It also needs an OR gate. Same thing, we have to change the number of inputs and the size of the symbol. Oops. There we go. Okay. So the nice thing about LogicSim, one of the nice things about LogicSim, is you can do a per input negation. So with this one, we can negate the top input pin, and then with this one, we can negate just the bottom input pin. So instead of using a NOT gate to do the negation, we can do it this way, which looks cleaner. It does exactly the same thing as using a NOT gate. It just looks cleaner. So now we hook up this one over here, and also over here, and then this one here, and over here. And then we take this to one of the inputs of the OR, take this one to the other input of the OR, and then this output becomes the output of the entire circuit. You can look at this circuit as a subroutine. So this is the definition of a subroutine. Every time you see an input pin, those are quote unquote input parameters. When you see an output pin, that's an output parameter. Okay? So that's one way to connect what you're seeing here to concepts that you have learned in cisp310. So I have just defined a subroutine, and doing this, turning into its appearance, is generating the prototype of a function. That's basically what it is. From the outside world, how do I make use of this thing? It needs two inputs and there's one output. Is that okay? So now I can go back to my half adder, and then I can say, oh, I can make use of my exclusive OR gate now because I just made one. That makes the R pin pretty easy to do, right? Because the R pin, the R is really just the exclusive OR between the X and the Y. So that is easy peasy. There we go. Are we good? So if you think about a subtractor and you think about a half subtractor, would the circuit need any changes at this point? No, because the result after a subtraction is exactly the same as the result after an addition. That's exactly the same. What about the carry? How did we implement a carry, which is an arithmetic concept, but in base 2, how do we use logic to do it instead? An AND gate. Very good. So we use an AND gate, okay, right here. And I think there's a way to change the default settings. I just cannot remember how to do it. So we use an AND gate to be my carry, and take X to connect it here, take Y and connect it over here. Now we have a half adder. So if I want to turn this into a half subtractor, what do I need to do? Instead of a carry, we have a borrow, right? So how is a borrow different from a carry? Yes?
You negate X before it goes in.
Yep, that's the only difference. Okay, so you put a little bubble here. Okay, so this is cool. This is my second level subroutine. I turn it into a function prototype. So I personally like to annotate the inputs and outputs. So we have the inputs are not as important because it's not a subtractor, so you can exchange the position without any bad things happening. But the output I really need to label because I don't want to mistakenly use one for the other one. So we have the result, we have the carry, and then the x and y we can just put it inside the box and make it look a little nicer and more compact. There we go. All right, so I have just made a half adder. Then the next thing I do is to implement or make a full adder. So I add another circuit, which is now a full adder. So a full adder is responsible for an entire column in a multi-digit addition. A half adder is only responsible for one half of the addition of a single column. So one would do the top, the other one would do the bottom. This is the full one. Okay, this one does both the top and the bottom. So when you look at the inputs to a full adder, we have an x bit. I'll call this xi, just so that it is generalized. We don't have to lock it to one particular position. This is yi, and it has a third one too. The third one is ki. In the case of an adder, in the case of a subtractor, we call it ti. Okay, there we go. And then there are two outputs coming out of it. For an adder, we have the sum bit, si. And also we have the carry to the next digit. So this is what we call our ki plus 1. Okay? So that's the interface to a full adder. Okay, we got 3 input pins and 2 output pins. We are looking at things from a vertical perspective, usually. So this is a different orientation of how we usually visualize a multi-digit addition. But the concept would still be the same. So I take out a half adder. Okay, we know that we need 2 of these, right? Now, how do I know I need 2 half adders in this circuit? Exactly. I call this a full adder, and I have a component called a half adder. That kind of tells you that I need 2 half adders in this circuit, right? Okay. So the first half adder connects just the xi and the yi. So it takes the xi, yi, like so. And there we go. All right. What is this? Does this have a particular representation in a multi-digit addition? What notation do I use? QI, very good. Good job. You guys are relating the kind of more abstract discussion with the circuit. Very good. That's QI. That is our QI. Exactly. Okay. How do we use QI? QI is an entirely internal construct that is not part of the output. So how do we use QI? There are 2 ways we use QI. Well, let's see. Now, there are 2 ways we use QI. What is the first way you use QI? How do we get QI to become the sum? It needs one more component. What else does it need? The carry. Okay, so QI and the carry, KI, somehow becomes the sum I, right? SI. How does it become SI? It's the R function, right? We apply the R function to QI and KI, and then the result of that R function is SI. Oh, we have another way to do an R? Sure, we can do it like this. Right? Let's take a look. We take QI, we take KI. Forget about the carry for now. We only want to use the R here. Isn't this R the result of adding QI and KI? That's just SI, that's sum. Okay, so we got one of the outputs right now. Very good. Okay. So now the next question is, what about ki plus 1? This one is supposed to go to the next column. Okay. Do you guys remember the equation of that? It's taking the carry of xi plus yi, right? And it also takes the carry of qi plus ki, and then do an or. Yep. So we got part of the carry here. We got part of the carry also over here. We're missing an OR gate. So we'll just take an OR gate. Okay, so here's an OR gate. And then we'll flip it this way. And connect that over here. So we just take one of these. It's going to look kind of ugly because I have to get around it somehow. There we go. And then we take the other one over here. There we go. Now we have a full adder. It is implementing all the logic that we need on one entire column of a multi-digit addition in base 2. Is that okay? We are close to running out of time, but we got 3 minutes. I think that's enough. All right, so let's label these pins here. We got the sum. We got the carry out. Okay, so I see this, call this carry out. C out. We got X, Y, and carry in. And I'm running short on time, so I'm not going to make it look nice. Okay, just functional enough to be used. So I go to main, and now I just, in order to make a 3x3 adder, I take 3 of these things. Okay, 1, and then duplicate it twice. Like so. And the carry out is the easy one to hook up, right? I mean, we know the carry out of 1 goes to the carry in of the next one. The carry out of 1 goes into the carry in of the next one. Yes? Okay. We know the sum bits are pretty easy to work with too. So we just have, sum 1, sum 0, S0, S1, S2 as the individual sum bits. There we go. And this one goes here. This is our K3. Okay, the K3 goes to its own pin, but it is not considered a part of the sum. Is that okay? All right, so I'm running out of time, but I just want to make sure that we know what to do with this. What about these things here? This one, C in, you can just hook it up to K0. Make a pin called K0. It becomes C in of the first full adder. This X goes to X0. This Y goes to Y0. X1, Y1, X2, Y2. That becomes a 3-bit by 3-bit adder, but it's a carry ripple adder, which basically means until this carry is determined, the result of this adder is questionable. Until the carry of this adder, full adder is determined, this adder is useless. And that's why there's a little daisy chain going on here, and that's why it takes so long for a carry ripple adder to finish adding. So what you'll be doing today is part 1 of a carry look ahead 3x3 adder. Do not use the design, okay? Almost no portion of what we talk about today in this carry ripple adder is actually useful in what you need to do at the lab. But this is kind of the solution that I want you guys to have for the carry ripple adder. And I can save it and share it with you guys later on, using announcements. So let me save it first, and then I'll share this with you later. All right, I'll see you guys over at the lab.